Okay, so this work is joint work with several colleagues. So Haixiang Zhang is actually work with me as a postdoc. And he is the first author of this paper, and he's a driving force behind this work. So now he's a associate professor at Tianjin University. And Xiu Mei and Xiaobin are faculty at Johns Hopkins University, so they provide the motivating data. Okay, and Yi Nan and Li Fang are my former colleague at Northwestern University, so that's where I started my work in the epigenetic study, like the high-dimensional mediation analysis. And Cheng is my colleague at University of Nebraska Medical Center, so he is an expert in causal inference. So that's why we rely on his expertise on this causality issue. Okay. Okay, so this is outline of my talk. First, I will introduce the background of this research and also provide our motivating example. Then I'll present our model and method. So in section 3, we'll show some simulation result to assess the performance of our method. And then we'll apply this, this method to a real data analysis. Finally, there are some conclusion remarks and extensions. Okay. So, so we are interested in the DNA methylation. So that's my work at Northwestern. So I collaborate with Dr. Li Fang Hou, and she's a molecular epigenetics. So she's interested in the DNA methylation analysis. So that's how we start working in this topic. So DNA methylation is a major epigenetic regulator of gene expression. Okay, so this DNA methylation is not like it will not change the sequence, DNA sequence. So you still have the same sequence, but rather it's a modify. It's just by adding the methyl group to this C5 position of the DNA base cytosine preceding a guanosine. So that's a sequence we call is a CpG dinucleotide. So by this addition, so it can change like a gene expression. Okay. So DNA methylation stands at the intersection of genetic and environmental risk factors for disease, and it's critical for improved risk prediction and biological understanding of chronic disease in this precision medicine era. Okay, so not like genetic variation. So like we know, like there's some, it's hard to change like the gene, right? The DNA sequence, like there's some, like for example, gene like a mutation, but this is mostly random. Okay, or you can do some like by gene therapy or like CRISPR or other more modern technique, but that's very expensive. Okay, and also like not like cannot be done like in our daily life. Okay, so that's so basically we do not change the DNA sequence, but rather like these environmental factors and human behavior can induce change like in the DNA methylation. Okay, so that's much easier to achieve. Okay, and these changes can also be modified through like preventive and therapeutic interventions. Okay, so methylation modifies the DNA function typically by suppressing gene transcription, which might change the cause of disease development. Okay, so in this sense, like DNA methylation may serve as a mediating factor in the causal pathway from the environmental exposure to phenotype. So here the exposure could be like smoking, drinking, exercise, diet, and other things like treatment. And the phenotype could be like lung function, BMI, disease incidence, and other health outcomes. Okay, so now this brings us like to the basic idea of mediation analysis. So actually, mediation analysis originated from like this social science. So this is the first paper by Byron and Kenny. Okay, so here we have this like this figure 1 show like a simple mediation analysis with a single mediator. Okay, so you have X as exposure, M as a mediator, and Y as an outcome. Okay, so we have an indirect effect. So the indirect effect is like go from X to M and Y. So let's go through this mediator. So that's the indirect effect. And we denote that this coefficient, if you regress M on X, you get this coefficient alpha. And if you regress Y on both M and X, you get this regression coefficient beta. So alpha times beta is the indirect effect. okay, often denoted by like alpha times beta as the indirect effect. Okay, there's also a like straight like arrow from x to y directly. So that is denoted by gamma. So that's the direct effect. And often in linear model, we can see the total effect is a sum between this indirect effect and the direct effect. So we can write this total effect as alpha times beta plus gamma. Okay, so that's the single mediation analysis. Okay. However, in our current situation, we have a high-dimensional mediators. Okay, and this often occur in modern biological and epidemiology study, like especially like in omics study, you can have like gene expression or metabolite levels and other like omics markers. Okay, and recent advances in measurement like tools have resulted in epigenome-wide DNA methylation data. We call EVAS data, and this has become the standard for studies of epigenetics in human populations. Okay, so recently Illumina they have this new array called EPIC array, so which can profile 850K DNA methylation markers. So that's almost double of the previous one, like the human methylation 450 bit chip. So that's can handle like 450K. Okay, so you can see this now we have a more a more higher like the dimension become higher and higher, and this ultra high dimensional EVAS data pose great challenges for conducting data analysis. Okay, so basically we need a more like advanced method to handle this the data analysis. Okay. Okay. So in this figure, we give like an illustration of the high dimensional mediators. So basically, instead of only one mediator, we now have a p mediator. So we have M1 through MP, and we have many p like actually indirect paths. So for M1, the indirect path is alpha 1 times beta 1, and up to this MP is alpha p times beta p. Okay. So this is illustration of the high dimensional mediators. Okay. So for this kind of mediation analysis in this high dimensional setting, okay, most of the pre-work they only focus on like the selected candidate messaging markers. Okay, so but recently there's a surge in high dimensional mediation analysis. Okay, so so this paper is also by the first author like Hai Xiang. So we propose a high dimensional mediation analysis. I think this is the maybe the first paper on this topic. And we also have this R package called HEMA. Okay, and this I think this method is well received. This package has been downloaded more than 30,000 times, and we have a lot of citations on this work. And then there's other work like including at least this is the incomplete list. I think that maybe like maybe 100 paper, maybe not 100, but quite a few papers on this topic. Okay, and we have done some work on the continue working on this area. Okay. Okay. So up to now, most of the existing works primarily consider the mean regression model. Okay. However, this mean-centric technique may not fully capture the mediation effect across the entire spectrum of outcome distribution. Okay. So there's one work by Shen et al. So they introduced like a quantile mediation model, okay, focusing on the outcome distribution, but they only have one mediator, a single mediator, not high-dimensional mediator. Okay, so given the prevalence of this high-dimensional data, so there's a urgent need to develop innovative system method for quantile mediation analysis that can accommodate high-dimensional mediators. Okay, so our goal is to develop a new method to identify potential mediators in the framework of high-dimensional quantile mediation analysis. Okay, so here we show our motivating example. So this is a birth cohort study. We examine 954 mother newborn pairs from a primarily urban low-income multi-ethnic U.S. birth cohort. Okay, so the dimension is very high. It's like 865,000 CPG size. Okay. So we use like the newborn cord blood DNA sample, okay? And Xu et al. Revealed that the newborn exposed to smoking weighed an average of like 258 grams less than their unexposed counterpart. Okay, so the smoking can reduce the birth weight. Okay. Furthermore, the impact of maternal smoking on offspring birth weight is mediated by demethylation, okay, as indicated by the mean regression models, okay. So our work is to study this mediation effect of demethylation specifically on the low birth weight, like we call LBW or high birth weight individual, like instead of only all those on average weight. So we have this. This is our path. So mother smoking, and then go through this demethylation as mediator, and then the outcome is like quantiles of birth weight. Okay. So I think most of us, like if you are parents, you are familiar with this kind of plot, right? This is actually is a CDC growth chart for girls. So that's from birth to 36 months. Okay. So when you visit, like you bring your child to your pediatricians, and they measure like the weight and height of the baby, and then they will tell you, okay, so for example, the baby is like now is 1 year old, and his weight is like maybe I just make up a number like 15 pounds, and his like his percentile like maybe like 25 percentile, right? So that means like for this weight and height, like it is important to to look at the quantiles, the percentiles. And here we show like this is this curve like 5%, 10%, 25, 50, 75, 90, 95%. Okay. So this is our motivation why we are interested in the quantile regression in this in the mediation analysis. Okay. So here is our model. Like we have this high dimensional quantile mediation model. Okay. So we have this. The first equation is actually we regress M, the mediator on the exposure. Okay. So M here because we have P mediators. Okay. So basically we have one equation. So equation one actually is just for one of the mediators. So basically we have a P equations in this model one. Okay. And this Mx represents the potential mediator that would have been observed if this x been set to the small x. Okay. And the z here is a covariate like age, gender, and other like confounders you want to adjust for. Okay. And in the second equation, we basically model the quantile of this outcome. Okay. So this Q tau y is a tau quantile of this outcome y. Okay. And then this yxm is the potential outcome that would have been observed if x is being set to small x, and m is being set to this small m. So this small m is like we have p mediators here. It's high dimensional vector mediators. Okay, and we have this error term in this in equation one. So this is our model for this high dimensional quantum mediation. Okay. Okay. So here we further explain. This is the same model. We just write it here, for you can look and see it clearly. Okay. So here we have alpha. Alpha is like the parameter related to the relating the exposure to the mediator. Okay. And gamma tau is the direct effect of x on the tau quantile y after adjusting for all the mediators and the covariates. Okay. And the beta tau is the vector parameter relating to the mediator to the tau quantile of the dependent variable, adjusting for the effect of the exposure and the covariate. Okay, and here eta tau and this zeta k is a regression coefficient for the covariate, like the confounder we want to adjust for. Okay, and then these two are the intercept terms. Okay, so this is the interpretation of this model, like the different part of this model.
Lei, I have a question.
Yeah.
So what's the order of P relative to N?
900 versus 800,000.
Okay.
The sample size? The sample size is 954. Yeah.
Is the mediator continuous or discrete?
It's a continuous. Yeah. Methylation is a continuous variable. Okay.
I have one quick question.
Yeah.
So in birth weight, when you do quantiles.
Yeah.
You're doing them as an ordered grouping, but in birth weight, low birth weight and very high birth weight are both considered adverse outcomes. So is it just strictly, this is just strictly an order thing and assumes that the bigger you are, they're separate, discrete?
So you mean do we force if there's order like 5% should be less than lower, lower than the 10th percentile. Is that
Right, but is the model assuming that?
we didn't make that assumption.
So there's no assumption of a direction?
No, we fit it separately, so we didn't make that constraint like in our model. Okay.
Is the notation all the same if you had a different outcome, either a binary, if you had a binary outcome in particular?
Well,
Just
binary
how,
outcome-
what does this change?
But here we have quantile, so basically
Yeah.
quantile is for the continuous order.
Yeah, but does all these methods you're going to show, would they have a similar application if you had a binary? I'm interested in binary outcomes. Does all this
Oh.
apply to binary, or is it a completely different tool?
You don't need this model for binary outcome. We have other model, like for example, we have logistic model for the binary outcome. So that's not in this paper, but we have that in, I think we have the in the R package, I think for the binary outcome. Yeah. Okay. So here goes like some of the assumptions to identify the causal effect. Okay, so this is maybe the for people not familiar with this causality, that may be something like maybe a little bit hard to understand. Yeah. So we just listed here like the first one is a stable unit treatment value assumption, so called SATVA. Okay, for short. Okay. So that means no multiple version of exposure and no interference between subject. Okay, so that means like the observed variables are identical to the potential variable corresponding to the actual observed exposure levels. Okay, so that's like no interference between subject means like there's you think that the people are independent of each other, they will not talk to each other like to receive like the interactive effect. Okay, and there are no C2 is no measurement error in the mediator and outcome, and the C3 is like the mediator are assumed to be causally independent. So that is does not allow that one mediator is a causal another. So they could be correlated, but you cannot like there's no situation like one mediator cause like the change in another mediator. Okay. And the last one actually is more complicated, is like assumptions on the confounding. So basically we have to assume like there's no unmeasured confounding between the exposure and the potential outcome, and no unmeasured confounding for the mediator outcome relationship after adjusting the exposure, and no unmeasured confounding for the exposure on all the mediators. Okay, the finally is no exposure induced confounding between the mediator and the potential outcome. Yeah, I know there's a lot of conditions, and I think it's really hard for me to explain very well on each of this. I mean, in a short time period. So I think you can read our paper. Also, like I have some illustration actually, maybe explain it better. But for now, I just like these are the assumptions we will keep in mind, and that help us derive like the estimation process. Okay. So now, like when we need to derive our estimate and our outcome of interest. Okay. So here we are interested in the controlled effect. Okay. So here is like we have this given the correct, we use this Q tau. Okay, to represent the tau's quantile of the conditional distribution of the potential outcome that would have been observed if X are set to X and M are set to this conditional expectation counterfactual. So basically you see this here, we didn't use this MX star, but we use the expectation of this, okay? So this is like make it a little bit different from, you may more familiar with like the natural direct effect or natural indirect effect. But so in that situation, there's no expectation here for those natural effect and natural indirect effect. We have to take this expectation because that helps us to derive this equation. Okay, so basically that's why we need this. We need this as the indirect effect, and that's to derive that we have to use this expectation instead of the MX star. Okay. Yeah. So under this assumption, so we have, this is our derivation, okay? So this is Q tau, okay, can be written in this way, okay? And this one actually is the indirect effect, okay? And we have this, actually this intercept, okay, can be written in this way. And this C2 is a effect of the compounder on this quantile, Tau's quantile can be written in this way. Yeah. So that's so basically you just plug what you do is like you can just plug the first equation, the expectation of the first equation into the second equation, and then you can derive this you can derive this equation here. Okay. The reason we need to use this E expectation is like we want to get rid of this EK term, because when you take the expectation, the EK disappear, right? So then we can just get that like the equality here. Okay. Yeah. Okay. Question.
The conditional expectation is actually estimated in the model with both Z and X, right? The M model,
What's that?
the model for the mediator. So given both Z and X.
You mean this one?
It's conditional on X and Z.
Yeah. Yeah. Actually, here, here we should condition on X and Z. Yeah, you're right. Yeah. Actually, in our paper, we write it in a more rigorous way. Here, I didn't write it the same as paper because we do have actually two conditions. Here we have condition on X and Z, and then we have another condition. So basically, we have two conditions. Okay. But I'm afraid when I write that way, that make it look so sophisticated. Yeah. So this is not the exact form as is shown in the paper. Yeah. Yeah. But you are right. We need to condition that, right? Yeah. Okay. Okay. So after we derive that, then we can easily to get the control direct effect and the control indirect effect. So basically, just use this is like the Q tau. So here is like you see, we fix the mediators like the X star, but then we study the difference between X and X star here, and this is the direct effect, and the indirect effect is like we fix the X the same, but then we change the X in this mediator here as X and X star, and then we get this one. Okay, so this is our indirect effect. Okay, so you can see then this multiplication, this is our just like what we have before, like the alpha times beta as the indirect effect. So that's why we have to make these assumptions, and we have to using this controlled effect to derive this term here. Okay. Okay. So this conditional indirect effect is can be expressed by alpha k times beta k tau. Okay, and this implies that the tau's conditional quantile y serves as the primary outcome of interest. Okay, and then we can use this to denote those like the index of statistical significant mediator at a given quantile level. Okay, and this number, so this number will be much smaller than the original dimension p. Okay, so that's often the case, like in the epigenetic studies. Okay.
Does it, can it increase with P? Although it's much smaller than P, can it increase with P? The number of significant features.
I'm not sure, like that's here P is it's fixed, like a different, like because we use this epic array, so it's fixed at this 850K. Yeah,
In theory, it's increasing with sample size, right? In theory.
you mean this is not some P is not sample size, right? P is,
But usually when we talk about high dimensional
yeah,
data analysis, P is some order of the sample size. For example, polynomial order or non-polynomial order of the sample size.
Yeah, that was actually a question that was asked earlier, the order of P with respect to N.
we didn't study that theoretical like derivation, like the theoretical properties. We didn't derive the asymptotics here. So that's our some actually you will see like from our own experience, like the final number of identified biomarker is only often less than 5. So it's much smaller. It's like only those very strong biomarker can survive. Yeah.
We can assume there is a upper bound for that number of significant features.
We don't assume that's upper bound, but this is just from our practical, experience. Like
Yeah, for these kind of applications, maybe
Yeah.
it's safe to assume it's upper bounded by something.
we didn't make any upper bound assumption. Yeah. Okay.
Can we consider tau as a tuning parameter of?
No, the tau is not tuning parameter. Tau is quantile. So we need to study, like, for example, fifth percentile, 10th percentile. Tau is not a tuning parameter. Tau is what we are interested in. Like, we just like the growth chart. We want to study like the quantile for each of these tau. Yeah. Okay. So now let's look at the estimation and the inference. Okay. So basically we have 3 steps. The first step is like do a screening. So this can be done like, because here we have a ultra high dimension, like 850K. So that's too much, too large, like compared to our sample size is usually below 1,000. So the first step is like we take the screening step. So we can reduce the dimension from like close to 1 million to like a number like to a few hundred. Okay, so it can be done by Schur independent screening. Okay, and second step is after we do the screening, we can have like a few hundred left, and then we will do like a penalized estimate on those like 100 in this 100 like mediators. Okay, remaining after step 1. Okay, and in step 3, like it's like we do a mediator selection. So basically, we can use like Jones significant test to test like this mediation effect. Okay. So the first step is like it's a mediator screening. Okay, so we first like in the variable selection process, we first like the standardized mediator to ensure the regression coefficient are on the same scale. Okay, and then we can do like this screening on this marginal quantile regression model. So note here we only have 1 mediator at a time. Okay, so basically we have this we do it p times. Okay, so each time we only include 1 mediator. So it's just like a marginal regression model. Okay, and then based on this marginal quantile screening theory, okay, so we can identify this subset. Okay, so those among the top D. So D is here is 2n over log n. Okay, mediators we have the largest beta value, estimate. Okay, and then we can reduce the dimension of the mediator from the P to D, like from like 850K to like a few hundred. Okay, and this ensures that the active mediator are returned with a probability of approaching 1. So by the theory, like the Schur independent screening theory. Okay. So second step, we do a penalized estimate. Okay, so this step we will do like we will do a variable selection for the mediators. Okay, by for those mediators left after screening. Okay, So we can minimize this penalty based criterion. Okay, so this is like this is the penalty term here, and the row tau here is actually is a check loss. So that's the check loss commonly used in the quantile regression. Okay, and this penalty term is like we penalize all the parameters in this vector. Okay, and there are many different ways to do this penalization. Okay, so here we take the MCP minimize concave penalty. Okay, and there are other things like you can do like maybe lasso or other like debarred lasso and SCAD. So there are many different selections, but we think this MCP has good properties. Okay, so here lambda is a tuning parameter, and the delta actually is a concavity parameter. Okay, so this one we take this because this has been implemented for the quantum in this paper, and we can use like the R package to solve this optimization problem. Okay, and then we use this S tau to denote index size of survived mediator after this step 2. Okay, so this one, so in this step we do a selection among those screened variables. Okay, so now we can further reduce this the set index set. Okay. Okay. So the third step is that we do selection. Okay. So step 2 can tell us which one is 0 and which one is not 0, but we cannot do inference. Okay. So it cannot provide us like the scenarios accurate scenario estimate. So basically in step 3, we first like we first refit this submodel. So basically we took all the parameters, the non-zero mediators in step 2, and then we refit it. So this time is by like a regular quantum regression model. Okay, so this is the S tau is a subset which index belong to the S tau. So that's what is remaining after step 2. Okay, so then we can get this parameter estimate for beta and the standard error in this model 7. Okay, and that easily can be done by this this quantum regression model. Okay. Okay. Sorry. Okay. So then the John significance type decision is like we can define this is like a D as a minimum of this first term and 1. So this D tau is the number of elements in this set. Okay, so this was how many are non-zero. Okay, and this P is the maximum of these two P values. So this is for the alpha and this is for the beta. Okay, so alpha is simple. It's just the ordinary square. When we regress each m on the exposure. Okay, and this P beta is like this is what we got from this previous this model fitting here. Okay. Okay. So then we can so basically you see basically we just do like a Bufferoni correction here because this D tau is a number of non-zero elements in this set. Okay, and D times this P is basically is kind of like a Bufferoni correction. Okay. So so then we declare these mediators are significant if this D is less than 0.05. Okay. And we so we have implemented in this like a function called Q HEMA. Okay, and this is in our package HEMA package. Okay, so you can download this package and run this on your data if you're interested in this model. Okay. 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 So now let's look at the simulation study. Okay. So this is the model for the mediator. So basically we regress M on the R on the X and the Z. Okay. So X is exposure, it follows the normal 0, 4. Okay. Cohort Z is like the independently generated from the from this normal distribution. okay? And the E here is like from a multivariate normal distribution, okay, with mean zero and the covariance matrix sigma. So basically, so that means these P mediators, they are correlated. So they have an AR1 correlation structure, and the rho is 0.25. Okay. And for the outcome Y, we actually have two settings. In the first setting, basically all the tau, all beta k tau are the same. So basically that means like this the effect is the same no matter your quantile. Okay. So basically we can rewrite this tau conditional quantile is given in this form. So you see here there's no gamma tau and there's no beta tau. So basically they are same for different tau. Okay. And in setting 2, here we have a different tau, a different beta k tau for different tau. Okay. So what we do is like here for the error term here, we add this term. So make it this heteroscedastic. So basically this big error variance will depend on x and m. Okay. So if we do that, then we can derive this q tau. So that you see here, this before x, we have this tau here. And before, we also have a tau here. Okay. So then if we define this r gamma tau equals this one, and this beta tau equals this one, so then we see we have a different tau. We have different beta for different quantiles. Okay. So this way we have this setting like the beta k tau is different. Okay, for different quantile. Okay. So this is like general setting of this model of the simulation study. So we have 500 data sets, replicates, and P is 3000, N is sample size 200, 300. Okay. So for alpha here, we have the first seven alphas are non-zero, and the remaining like are zero. So basically, you see P equals 3000. So basically, the first seven are non-zero, and the rest are zero. And beta is have this parameters. Okay. So look at if you take alpha times beta, then the first three are quite large, right? If you take alpha times beta, the first three are large, and the fourth and fifth one are small, right? If you take like for example 0.15 times 0.25 is a small number, and so is the fifth one, and the rest are the zero. Okay. So what we see here is like also the eta here, eta is sorry, the phi here is the first three are non-zero and the rest are zero. Okay. So overall, we have the first the 5 meteors have non-zero effect, right? So the first 5 alpha times beta are non-zero. 3 are strong, so the first 3 are strong, and the 2 are weak in terms of the magnitude of indirect effect here. Okay. So this is our model generating setting, and we also compare to another model by Shen et al. So that's a single mediator model. Okay. So what they do is like simple. It's just like they fit each mediator separately in this quantile regression. Okay, and then they do like a Bufferoni correction for this p-value. Okay. So this q tau depend on only one mediator in each model. Okay, but there's some disadvantage of this method. So it's first it failed to adjust for other p-1 mediators, and this could lead to either inefficiency because if the mediators are independent of each other, or even bias if the mediators are correlated. So you have a multicollinearity problem. Okay, and later may be more troublesome because the correlation among the CPG sites are close. They could be high correlation, like as high as 0.6, and or could be like in the blood sample, it could be like almost 1, it's 0.98 in our data. Okay. Another disadvantage is like you cannot predict this y, like the quantile y, q, using only one mediator, right? Because we have so many mediators for prediction, you have to include all of them in your model. Okay. So here we show the result. So basically, we see that this is the bias and the standard deviation of the estimate for this mediation effect. So this is our first setting, okay? And if you compare the Shen's model and our model, you see actually our model have a smaller bias, okay? And for each settings, and here we see this is different tau, like 0.05, 0.25, 0.5. So this is median, okay? And we calculate this alpha 1 times beta 1 tau, okay, for each of these, for the first six mediators, okay? And you see like this, we have this here is we show the tau is 0.75 and 0.95, okay? So across all taus, we see our method actually perform better than the single mediator model by Shen et al. Okay. And this is setting 1. Here we show the setting 2. Okay. Again, you see like we have a so in the setting 2, like this beta tau are different. Okay. Beta 1 tau. This for different tau, like the beta. This one is different. Like this one is different from this one because we have different tau. Okay. So, but again, you see our model perform better than Shen's et al.'s method. Okay. Okay. So another measure is like is the accuracy of mediator selection. Okay. So we use 3 criterions. So the first one is the model size. Okay. So that is the number of elements we selected. Okay. The second one is TPP, the true positive proportion. So how many among those true mediators, how many we choose? Okay, what percentage we choose? And the last one is the false discovery rate. So among what we choose, how many are false positives? Okay, so we present the result here. This is for the case 1. Okay, so you see, so compare our model to Shen's model. Okay, so you see we choose more mediators than they did. Okay, and this MS is larger in our model than in their model. And the TPP, the true positive proportion, is higher in our model. And FDP, actually, they are smaller, but our is pretty good. Like it's below 0.05, right? So this is like this is well below the 0.05. Okay. So their method seems too conservative because you see their FDP is too small. Okay, so that actually is too conservative. So as a result, the TPP is smaller. Okay, compared to our method.
So I have a question. Did you in settings where the correlation among the mediator is a little bit high? Did you look at that case?
Okay. Yeah.
You know, when the association among the mediator is high.
Oh.
I think you use an AR1 process.
Yeah, we didn't consider other correlation. We only use correlation 0.25. Yeah, but yeah, we can try other like rho equals other numbers. Yeah, but we didn't consider that in here in the simulation study. Yeah. Okay. Okay. So this is in case 2, and again we find our model is better, like in terms of the how many variables we identify. Okay, and the true positive proportion and the false discovery proportion. Okay. Okay, so the summary. So this table 3 to 4 presents the mediator selection result in the term of the model size, TPP and FDP. So this suggests that Shen et al. Tend to select a smaller model with lower TPP and FDP. So that their method is more conservative than our procedure. So the overall, the proposed mediator selection method works well for high-dimensional quantile regression. Okay, in this simulation study. Okay. So next, we apply this to a real data set, the birth cohort study of mother-newborn pairs. Okay. So each year in the US, the maternal smoking affects over 500,000 pregnancies, and this results in fetal growth limitations and reduced birth rate. Okay, and it's following like long-term implications. Okay, and we apply our method to a birth cohort comprising like 954 mother-newborn pairs from a predominantly urban, low-income, multi-ethnic birth cohort in Boston. Okay. And among the mothers, about 17% had a history of smoking either before or during pregnancy. and the newborn exposed to smoking exhibited an average birth weight reduction of 258 grams compared to those without exposure. Okay. So in this epigenetic study, we profile like 865,000 DNA methylation markers. Okay. And we use that as a potential mediators. The outcome is like birth weight at different quantiles. Okay. And the exposure X is smoking status. So basically, it's binary. It's 1 is smoker and 0 is non-smoker. Okay. And we interested in examining the mediation effect across the entire spectrum of the outcome distribution. So specifically on the low birth weight and high birth weight samples. Okay. So by the low birth weight, we mean we take the tau equals the quantile as 0.2 and 0.3 as low birth weight, and the high birth weight tau equals 0.7 and 0.8. Okay, and then the tau equals 0.4, 0.5, 0.6 as the normal weight group. Okay. So we also adjust for other cohorts like that include maternal age and parity. So that is how many previous births. Okay, and maternal education, maternal self-reported rates, and maternal alcohol consumption during pregnancy, and maternal pre-pregnancy BMI, child sex, and gestational age at birth. And as last one is estimated cord blood cell composition. Okay, so there are 7 cell types in the blood. Okay, so this is 7 types, and we have this we use this composition as a cohort in our model. Okay, so this is a histogram of infant birth weight. So you see there's like quite few like a low birth weight group here, like somehow even like less than 1,000 grams. Okay. Okay, so this is a summary from our model. Okay, so what we see here is like this at different tau we identify different CPGs. So this is like at tau equal 0.2 we identify these two CPGs, and at 0.3 we identify this one. Okay, and in average like when for normal birth weight you can see we identify this one for these 3 tau level. So this is quite consistent at this average, the normal birth weight group. Okay, we identify the same CPGs. Okay, and this one is we cannot identify anyone for tau equals 0.7, but we identify 2 for tau equals 0.8. Okay. Okay. So we see the different medians are identified at different quantiles. Okay. So at tau equals 0.2, so that's a low birth weight group, we identify 2. Okay. And tau equals 0.3, we identify like another one. Okay. And at the normal weight group, okay, the regular weight group, 1 CPG is consistent as in one. Okay. But at tau equals 0.8, our method identify these 2. Okay. But if you apply this Shen's et al. Method to this data set, you will not identify any significant mediators. Okay, after you adjust for multiple comparisons. Okay.
So the identification of these different CPGs, is that having any impact on the direct effect of smoking? I mean, are these impacting?
This is indirect effect.
It's an interaction effect.
Indirect effect.
Indirect, yeah.
Yeah.
But accounting for this indirect effect, does that have any impact on the direct effect of smoking? I mean, would you see a different direct effect across different quantiles of birth weight because of these mediators?
We didn't show that result. I think you probably will have a different estimate for direct effect in each of this model, in each of these tau. Yeah, because we fit a different model for different tau. So the direct effect may be different. Yeah.
The total effect might be the same.
For different tau may be different too. Yeah. Okay. Okay.
I think that's related to the here when we do the analysis, we show only the alpha head, beta head.
Yeah.
And you have this gamma head each time as well,
Yeah,
right?
right.
So I think that addressed that question. when we do different quantile, does the gamma had changed?
Yeah, I think that may different, maybe different. Yeah, so if you look at this, in our,
Maybe like really
yeah, this one,
Yeah.
believe it or.
yeah, that may be different. Okay. Okay, so here are like, we check the literature and find like, whether our result is consistent with like scientific finding from other people. Okay, so we find like this, the effect of maternal smoking on birth weight is partly mediated by this methylation of this CpG at this P1 PIM1. So that is the first one here, this one. Okay, so this identified by other people. Okay. Okay, which contribute to the decrease in birth weight. Okay, and also the several studies show that the maternal smoking may influence DNA methylation at this key, so this KRF13. So this one and all this one. So this is like common one identified by several quantum levels. Okay. Yeah. Okay. So additionally, the association between this methylation, KRF13 methylation and smoking may have implication for childbirth and the development of the metabolic syndrome. Okay. So on the tau as high birth weight group, we identify the two CpG sites. Okay. So actually the second one is is of our interest because in our previous study, we also identified this one as a mediator in the path from smoking to lung function. Yeah, so in our 2016 paper, we also identified that one. Okay, so here we identified like the significant mediating effect in the high quantile between between smoking and the birth weight, and in the low in the high birth weight group. Okay, but this one does not show like for the mediation effect in the low birth weight group on median. Okay. So this is like this CpG, okay, is in the AHRR gene has been robustly associated with smoking, okay, and which is thought to mediate the association between maternal smoking and the metabolic profile in children, okay, and this demonstrates the capability of a model to thoroughly capture the complex mediating effect across different sections of the outcome distribution, okay. Okay. So here are some concluding remarks. So we propose like a novel high-dimensional quantum mediation model, and we use like screening procedure to address the ultra high-dimensional issue in this DNA methylation marker. Okay, and we use the MCP method and the joint significant test to identify significant mediators, and we show the simulation study that our model has a good performance, and then we apply this to a real data. Okay. Here are some future directions. So first one is like how to account for the high correlation between methylation markers in the close proximity. Okay, so this way we can improve the analytical validity. So I think that's a question related to David. Yeah. So probably we can use a conditional SIS, conditional true independent screening method to reduce this the impact of the correlation. Okay. And second one is like in addition to the high dimensional mediator, we have multiple exposures of interest, like different type of food intake and different genes. Okay. And there's another paper actually they applied functional regression to both mediator and outcome, although this is in the single mediator setting. Okay, so we can also extend this into a high dimensional mediator setting. And then it's like how do we handle the longitudinal data with repeated measure for mediators? Okay, so actually, in our current study, like we have 4 time points. Like we measure the mediator DNA methylation at 4 time points. So how to incorporate that longitudinal mediators, a high dimensional mediator is another topic of interest. Okay, and again, this causality issue, like here, actually, this is a observational study. with a non-randomized exposure. Okay, so in this setting, probably we have to maybe use like either use some propensity score matching or some other method to capture this to address this observational study, the causality issue. Okay. And finally, I show some of my other research interests. So first is like so this is a joint model of multi-outcome. That's actually, I started that when I was a graduate student. So we have published quite a few papers, but more recently, we are interested in how to link this joint model with mediation analysis. So we have two papers, actually, we kind of think this longitudinal biomarker of recurrent event as a mediator for the survival outcome, as for example, for death, okay? So we have two publications, you can check that out, okay? If you are interested, both joint model and the mediation analysis, how can we link them together? And I also am, as Chen Xi introduced, I'm like a chair of this internal groups workshop on the, we call it SAM, okay, SAM workshop, okay, so you're welcome to join us like in Salzburg this year in July, okay. I'm also interested in like zero inflated continuous data like medical costs, alcohol drinking, microbiome, and single cell. Actually, I'm working on a book like on the analysis of medical cost data, with my colleague, okay, on this topic. And then we are interested in precision medicine. So basically, we would like to identify subgroups in pharmacogenetic trials, like for Alzheimer's disease, pharmaceutical trials, like. So we know like most of the pharmaceutical, like the Alzheimer's trials, they failed, right? So there's no difference between the treatment and placebo. So we think maybe there are some subgroups which have positive effect. And by the other group, they have negative effect. So then when you add up, they cancel out each other. So overall, there's no effect. So that's why we would like to see whether we can use use, for example, use some interaction tree-based method to identify those subgroups. Okay. So basically, then we can try this medication on those these subgroups only, not on the general diseased people. Okay. Finally, my recent interest is like integrate deep learning with traditional method like the survival analysis. Okay. Okay, and this is the funding support, and thank you. Okay.